All right, welcome back. So today we are going to continue looking into chapter 18. We'll be talking about electric field and the way to represent it, electric field lines. Okay, so we'll have a quick review from what we learned last time. Um, and so last time we talked about charges. There are two types of charges, positive charge and negative charge. So like charges repel each other and opposite charges attract each other. Okay, so SI unit for electric charges are coulombs, capital C, and typically use small q for charge. Or you can also use large Q, but since we just got out from thermodynamics, so larger Q was used for the heat. So we will stick, with small q for a little while. Okay, but you might see some other textbook use capital Q. That's fine. And charge is not continuous; it's actually discrete and quantized. So the minimum units of charge is the charge that an electron carries. So it's called electron charge. It's 1.6 times 10 to the minus 19 coulombs. An electron should have minus of that. Now proton on the other side should be having positive of that. Okay. These are some certain constant numbers that you guys may be using in your problem. We also talk about conductor and insulator. So basically, the two are different because they, for conductors, they do have conduction electrons. On the other hand, for inductors, they do not have conduction electrons. Okay, you can charge a particle by contact of it with a charged particle, or you can do charge by induction. So there's a couple of ways and that you can do it. Okay. We also talk about the interaction between charges. So if you have two charges, Q1, Q2, then the force between them is either positive or it's either attractive or repulsive. So depends on their charge. If they are like charge, then repulsive. If they are opposite charge, then the force will be attractive. But the magnitude of force is K, absolute value of Q1 and absolute value of Q2, and divided by R squared. R is the separation of the two charges. Q1, Q2 are the charges of the two. K is the constant called Coulomb's constant, is basically 9 times 10 to the ninth. Okay, in newtons times meter square over Coulomb square. So like charges, they will repel each other in these two cases, and then opposite charges, they will attract each other. So this case being attractive, A and C being repulsive. Okay. If you have more than two charges or multiple charges, then force on a particular charge should be the force of all the other charges on that one and add up. And remember, forces are vectors, so then you need to do vector additions. Okay, so either do component method or triangle method. So today we're going to look at the new concept called electric field. So this is in some way very similar to the gravitational force. We mentioned this in last class. So in gravitational force, because the formula is G m1 m2 over r squared, and then for electric force is K q1 q2 over r squared. So both are very similar to each other. So then for the electric force, here, if you have a charge like this, so this is for gravitational force, okay? So, but it could be similar to the electric field. So if you have a bigger m, right, then a small m nearby will receive the gravitational force G m1 or capital M small m over r squared, in which case that force is just proportional to the mass of this small one, and F equal to mg. So think about this as the Earth, and then this is any object nearby the Earth. So F equal to mg, right? So gravitational force in that sense. For electric field or electric force, it could be similar. Now, in the place of mass, you will be having the charges. So F equal to K, Q1, Q2. In this case, we call this Q, positive Q. This typically is a bigger one. And Q0 is a small one. So just similar to the in the figure in the previous slide, you have a bigger mass and a small mass, okay, in that sense. This small mass Q then is called test Q, test charge Q. So then force on this test charge Q then will be just equal to Q times a term constant here, E, which is similar to G, gravitational acceleration. In this case, it would be E, electric field. And electric field is equal to K Q over R squared, our absolute value of Q. Okay, so in this case, because this force is the same as this force, and then you compare the two, Q naught will cancel. Okay, so positive test charge I typically pick as positive, so that can cancel. So then electric field by this source charge plus Q will be KQ over R squared. Okay. Again, if you remember in the gravitational field, small g actually is equal to capital G times capital M over R squared. So again, pretty similar to this guy. Okay. So then we introduce this concept of electric field here by a point charge will be KQ over R squared. Okay. R is how far you are away from the source of Q. K is the constant of 9 times 10 to the 9. And then Q will be the charge on that source. So electric field, similar to gravitational field, it's a vector. It has direction. So it's basically equal to the electric force divided by the test charge Q0. And Q0 is normally a positive one that serves as how to calculate this electric field. Okay. SI unit for electric field is newtons over coulombs because this is in newtons, this is in coulombs. If you have, so then if you know your electric field, you can calculate the force because field is F over Q. So then force is Q times E. Okay. So similar to F equal to mg, in this case now Q could have positive sign or negative sign. So it's two ways. In the case of mass is normally just positive. Okay. Unless we are talking about antimatters, which is not the scope of this class. But F equal to QE, so sometimes that force could be in the same direction as the electric field, and sometimes it could be in the opposite direction of the electric field. So if electric field is pointing to the right here, if you have negative charge, then the force on the negative charge will be in the opposite direction. Okay. All right. If we have a positive charge here, and then if we have a test charge positive as well, so then E is going to be pointing away from this charge because force for the two will be repulsive, and then E is equal to force divided by this positive Q, so it'll be in the same direction in that case. Okay, so for positive charge, it will produce an electric field that is pointing away from it. Okay, so radially away from it. Now, if you have negative charge, then the electric field is pointing towards the negative charge. Okay, so electric field produced by a negative charge is pointing towards it. Electric field produced by a positive charge pointing away from it. The magnitude of the force, electric field, is the electric force divided by Q. So KQ, Q1, Q2 in that sense over R squared over Q. If you call this 2, or in this case it's Q0. So Q0 cancel. Magnitude will be KQ over R squared. Okay. So for point charge, electric field is KQ over R squared for the magnitude. Okay. And then depends on the sign of the Q. It could be pointing towards the charge, it could be pointing away from the charge. Okay. This is very similar to the force. Force is KQ1, Q2 over R squared, but this case you just have one Q. Okay, for the electric field. If you have multiple source point charges, like if you have I could be equal to any number, right? So then at a particular point of interest, you will have electric field produced by every single of that Q of I. So then E will be in that direction. And then if you have another source point, let's say somewhere here, it'll be in this direction. So for electric field at this particular point, then it will be the electric field by each individual charges add up. Okay. So again, electric fields, it's a vector. So then we are doing vector addition. Okay. It's similar to the force. Electric force is a vector. If you are adding electric forces up, we are doing vector addition. All right, let's take a look on this first example of the day. I'm going to switch my screen here. So then you can see how we can solve this one. All right. So this one says you have 2-point charges lie on the x-axis. So we can sketch the problem. We can draw the x-axis. It says a charge of positive 2.40 PC for picocoulomb. It's at the origin. So let's pick our origin. Let's say here is our origin, x equal to 0. Okay, so x equal to 0. And this charge is positive, positive of 2.40 PC. And it says a negative 4.8, so it's twice of the first one. It's at x equal to minus 10, so this is minus 10 centimeter. And then this is minus 4.8 PC. Okay. And then it's asking what would be the third charge should be placed. What third charge should be placed at x equal to 20? So x equal to 20. So then total electric field at x equal to 0, x equal to 10 will be 0. So here x equal to 10. So E field at here should be equal to 0. Okay. So we have charge. So this is the Q3 we are looking for. All right. There's Q1, Q2. So Q1 is positive, so we can take a look at the just the electric field produced by that first one here. So then it will be, because it's positive, it's be pointing away. So at this source of point of interest is going to point away in that direction. Now this Q2 here, it will produce an electric field at that point again, but it's negative, so it's pointing towards the Q2. Okay, so this guy will be E1, this guy will be E2. Okay, and then now let's see which one, like this Q3 will produce, it depends on the sign of this guy, right? So you'll produce an electric field either in a positive direction at this here or in a negative direction. Okay, so either way depends on the sign, because if this is positive, Q3 is positive, then it's going to be pointing away. So that means in the negative direction here. And then if it's negative of Q3, then it's going to be in this direction. Okay, so we don't know yet right now. So that's just maybe erase those for now. We'll have to compare our E1 and E2, see the magnitude because they are pointing in opposite direction. Just compare like which one has a bigger magnitude. Okay, so although I have this guy E1 as longer because I knew it, but we will see. So E1 for its magnitude, E1's magnitude should be K absolute value of Q1 because Q1 is positive, so it will be just KQ1 over R1. Okay, so K is constant, Q1 is 2.4, Q1 is this guy, 2.4 picocoulomb, and then R1 will be from here to here. So this is R1. Well, let me change the color. So for R1 is this guy, this is R1. R2 is from here to here. Okay, so R2 is there. Now R1 is 10 centimeter because this guy is 10. Okay, so this one is at 10. This is at 10. So R1 will be then just equal to 10 centimeter. R2 is actually 20. Okay, so so for the E2 then is K absolute value of Q2 because Q2 is negative over R2. Okay, now it's clear that Q2 is twice of Q1, so then this guy will be equal to K of times 2 times Q1. Okay, divided by R2 is also twice of the R2 is also twice of R1, so then this guy will be twice of R1. And I'm forgetting something here, I just realized, because E1 should be KQ1 over R1 square. And then E2 should be KQ2 over R2 square. Okay, so that means here we need to square here in the denominator layer. Okay. All right. So if we square the denominator here, it will give you 4 in the denominator. So twice of KQ1 over 4 R1 square. Okay. So then you can see 2 and 4 will cancel partially. So this guy is equal to 1/2 times KQ1 over R1 square. Okay. So this is then you can see E1 is KQ1 R1 KQ1 over R1 square. E2 is this guy. So E2 is actually just half of E1. Okay, so E2 is actually smaller than E1. So that's why I actually intentionally draw that E2 is shorter than E1. Okay, so then in order to have the E at x equal to 10 to be 0, so then E3 must go in the direction of in this direction. So E3 must be in this direction. Okay, so E3, that will be E3. And because E2 is 1/2 of E1, so E3 then should be also 1/2 so that they can cancel. Okay, so we can see that E3, its magnitude then should be also just 1/2 of E1, which would tell you this should be just 1/2 of KQ1 over R1 square. Okay, now E3 itself, if we just write in terms of KQ3 over R3 square. Okay, so we know that E3 electric field observed one should be in the opposite direction of E1, so that means it's pointing away from Q3. So then Q3 should be positive, right? Q3 is going to be positive. Okay. So then K absolute value of Q3 should be just Q3 because it's positive. Okay, and this guy and this guy is equal to each other, so you can see K and K will cancel at some point, but for R3 is from here to here. So R3 is also 10. It's 20 minus 10 is also 10. Okay. So R3 and R1 are actually basically the same. Okay. So R1 and R3 is the same. So here then going back here, so then this will be equal to KQ3 over R1 squared. Okay. So if we compare these two to each other because they are the same thing, so we can see that K will cancel, right? K and K will cancel. R1 square will cancel. So then you are having just Q3 here left, and then over here is 1/2 of Q1. Okay, so that tells you your Q3. Oops, your Q3. Then it's 1/2 of Q1. Okay, which then because Q1 is 2.4, then Q3 is just 1.2. Okay, picocoulombs, and it should be positive. Okay, because we know that the direction should be in the pointing away from Q3, so it's going to be positive. All right, so that's how we can solve for this one. All right, and then let's go back to the slide. Okay, so next one, we'll actually look at a second example. So I'm sorry about it. I did not have to actually go back to the slide, but we can go back to the a problem here. So, okay, going back to there. And then we're going to just move to the next problem here I have on this screen over here. Okay, so this one says that an electron has initial velocity of 2.00 times 10 to the 6 meters per second in the positive x direction. It enters a region that has a uniform electric field in the positive y direction. The electric field E is equal to 300 newtons over coulombs. It's asking you to find the acceleration of the electron. And then B, how long does it take for the electron to travel the distance of 10 centimeters in the positive x direction? And C, through what angle and in what direction is the electron deflected? Okay, so let's analyze this. So this is an electron. So as it is in the electric field, so then it will experience electric force. Okay, so electric force here, F, because field is going downward, so F should be going upward because this electron is negatively charged. Okay, so F is going to be in that direction, which will be equal to Q times E. For the electron is E times the capital E, so small e times capital E. Okay, so that's the force on the electron. So you can see electron then will be as it goes through here. So this is like kind of like a projectile motion. You have gravity here now in the form of electric force or electric field. It's pointing now actually upward. The force is pointing upward. So if this is a projectile motion, then this guy will actually go downward, right? So this guy will go actually downward, but because this is a projectile motion, so this force now is pointing upward, so this guy will actually go in that way, kind of like that way, okay, or close to that, just projectile motion going upward, okay. So the force is there. So in A, then we are looking for acceleration. Then it will be just the force of E, which means electric force, divided by the mass of the electron. Okay. Force is Q, which is E times net E, divided by mass of electron. Okay. Now we are given capital E as 300. Do we know small e? Small e is the charge of the electron, so it's a constant number. Okay. So we actually do know that. So we can use that. So E is 1.6 times 10 to the negative 19. So then in this case, running out of space, and let me just write down here, A equal to 1.6 times 10 to the minus 19 times 300. Okay. And then the mass of electron, it's also a constant number you can use. Okay. So it's 9.11 10 to the negative 31 kilograms. Make sure we have everything in kilogram. So this will give us 5.269 times 10 to the 13 meters per second square. Okay. And the direction, it's going to be, so in the problem, it says electric field is in the positive y direction. So that means going upward is the negative y. Okay, so this guy is the positive y. So upward is negative y. So we know that the direction of this guy should be in the negative y direction. Okay, so we can use that. Maybe use the unit vector like that. Okay. So this one is like unit vector, so negative y direction. So because it's looking for oscillation, it's a vector. So this is the magnitude, and that's the direction. Okay, so that's the our oscillation. So then maybe this guy is covered a little bit here. So like to 13 there. Okay. All right. So that's part A. Part B is asking you how long does it take for the electron to travel 10 in the x direction. So in x direction, if it travels 10 centimeters, how long is this going to take? So This projectile motion projectiling upward, so x direction should be just independent of itself, right? So x is equal to 10. So to find that time t that it takes, we should be just doing, so in B, we should be just doing t will be just equal to x divided by its velocity in x direction, right? The force is in y direction, so x direction velocity shouldn't be changed. So that means this guy is going to be just the original v0 that's given, okay? 10 centimeter, that means 10 to the minus 2 meters over the original velocity given in the problem, 2.0010 to the 6 meters per second, okay? So this will give you about 5.0010 to the minus 8 second, okay, on that. So that's how much time it takes. All right. Let's take a look on the last question. It's asking, it says, through what angle is the electron deflected after traveling 10 in the x direction? Okay, so after traveling in here, so it'll be somewhere here. Now it's going in that direction. V is in that direction. Okay, it should have an x component, V of x, right? Which is the original V0, because in the x direction, it shouldn't be changing. There's no force there. Y direction, then it will be in this direction, V of y. Okay, so we got the acceleration in A. That is indeed the acceleration in y direction, because the acceleration is only in the negative y direction, right? So then we can find what will be V of y, and then this angle at what angle theta then can be calculated. Okay, it will be just the y component over the x component of velocity, right? So we can look for the v of y, which then will be a of y times the t that we had in part B. So in this case, a is 5.269 10 to the 13 meters per second square, and then we will multiply that by the 5.0010 to the minus 8 second. Okay, so that will give us 2.63 times 10 to the 6 meters per second. Okay, and just keep in mind this is negative. Okay, so if you want, we can put a negative sign here, and then negative sign there, because it's the negative y direction. This will be in the y direction. So then angle theta is tangent inverse of Vy over V of X. I'm having trouble getting there, but all right. So tangent inverse of this minus 2.63 over 2, because they are both times 10 to the 6. So you don't necessarily have to write them down. They will cancel, okay, anyways, but it's okay if you do. So this will give negative of 52.7 degrees. Okay, so that's the angle at what angle is coming out, okay, on that one. All right, so that's how you will solve for this problem. Okay, see if we can zoom in a little bit so you can see everything together. All right, now we are going back to the slide. Okay, so we have seen in the examples or a few couple of slides earlier that electric field will be represented by lines with arrows, right? So the arrows indicate direction, and the lines will be representing the electric field. But So those are called electric field lines. Okay, so kind of like we have seen them first and then introduce the concept. Okay, so those are actually imaginary lines. We don't normally see the lines coming out of charges, okay, or coming into the charge, but those are imaginary lines for us to visualize the electric field, okay? So a few key points drawing the electric field lines. So they point in the direction of the field vectors, okay, at any point, just indicate the direction of the field at that point. And they will start at positive charges in the case that there's a positive charge. If there's no positive charge, then they will start from infinity. And the same thing, they will end at negative charges because the electric field lines, electric field are pointing towards the negative charges. Or if there's no negative charges, then they will be coming from infinity. Okay. Now, if you have a stronger field, then you will draw more line, okay? And in that region, then if you have weak field, if at some point, different locations, okay? Let's take a look at some examples. So if we just have a positive charge in the space and nothing else nearby, so then the electric field lines will be pointing away from that positive charge. So they are going away, okay? And then on the other hand, and then they will end at infinity. So they are pointing to infinity, towards infinity, okay? And if you have negative charges, in this case, twice as many, so then electric field are pointing towards negative charges, and they are coming from infinity, okay? So they start at infinity, pointing towards the negative charge. But in this case, these two cases, because this is just one Q, this is two Q, so you'll have twice as many electric field lines surrounding the charge than this guy. Okay, so this guy has 8, then this guy will have then 16. If you have a couple of charges in space, say a positive and negative, so then field lines will start from the positive and then pointing towards infinity or the negative charge, and then field lines will come from either the positive charge or coming from infinity and then pointing towards the negative charge. Okay, so if these two are equal amount of charges, just different opposite signs, so then the same amount of lines you'll be drawing surrounding the charges here and there. Okay. And if you have now, say, opposite charges, and then one is twice as many of the other one, so at a more charged location, you have more field lines or the lines than these guys here. And then again, starting from positive charge pointing to negative charge, okay? If you have like charge, the same amount of charges, then for example, positive and positive, so then they will come out from positive side pointing towards infinity. In the middle here, there's no line, so that means there's electric field at the middle is 0 because electric field produced by the left charge cancels out electric field produced by the right charge. Okay. All right. We'll take a look at a couple examples and then we'll move on from there. Okay, so let me just switch back to my other screen here so I can work on the example. Okay, so the first one here, it says the electric field lines surrounding the 3 charges are shown here, Q1, Q2, and Q3. The center charge is Q2 is given minus 22.8 microcoulomb. It's asking what are the signs of Q1 and Q3, and then B find Q1 and C find Q3. Okay. So if we look at the charges here, Q1 is negative, so electric field lines are going into Q2 or I'm talking about Q2 is negative, so electric field lines are going into Q2. Okay. And for Q3 and Q1, so you see electric field lines coming out from them, right? So then that means they are both positive sign, okay? Because electric field lines coming out from positive, okay? So for A, then kind of straightforward. So they are positive. Q1, let's say Q1 is positive, and then Q3 is also positive, okay? So Now B, find Q1. So we'll count how many electric field lines are surrounding Q1. So in this case, 1, 2, 3, 4. And then on the other side also 4. So there's 8 field lines there. On Q2, there's 1, 2, 3, 4, 5, 6, 7, 8 on the left-hand side, and then also 1, 2, 3, 4, 5, 6, 7, 8 on the other side. So total is 16. Okay. So that means Q2 is twice the charge of Q1. Okay. So then you can see Q1 then is twice of Q2. Q2 is minus of that, but Q1 is positive. So Q1 should be 1/2 of that. So 22.8 divided by 2 is 11.4. So then Q1 is equal to 22.8 over 2, which will be 11.4 microcoulombs. Okay, so it's microcoulombs. Let's erase some of this. It's like stacking all together. 11.4. Okay, microcoulomb. The same, you can count how many lines are on surrounding Q3. So again, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 8 again. So that tells you Q3 is the same as Q1 because they are having the same number of electric field lines surrounding it. Okay, so it's that. Okay, so that's how you can determine that. All right, so that's the first one, and then we will take a look at second one. Okay, so just to reinforce our knowledge there. So again, there are 3 charges here: Q1A, QB, QC, and there are field electric field lines either coming into them or out of them. So you can see. So the first question is asking again, which ones are positive, which ones negative, right? So QA lines are coming out, so then we know QA is going to be positive, right? So QA is going to be positive. QB charges going into it, so it's going to be negative. QC, again, lines are going out, so it's going to be positive, okay? So we can say, all right, so for A, QA, and QB, let's rewrite it. They are, or actually QC, sorry. QA and QC, they are positive, right? And then QB, that is negative, okay? B, rank the charges in order of increasing magnitude. So just magnitude, no worry about the signs, okay? So A has the fewest lines, 5, and then B has the second amount of lines, and then C has the most, okay? So then it's in the order of A is less than B, less than C in that order, okay? So kind of straightforward from there. All right, so we'll go back to the slide. Okay. Moving on to the next section, it talks about electric forces in biology. So in our body or any body of animals or plants, so there's a lot of molecules there, charged molecules. Okay, and then we know that nerve signal are going through the electric signals in that case. Okay, as well. So then one example would be DNA is actually highly charged molecules. So they have negative charges, so they repel each other, so they form this structure, okay, of double helix. All right. Water molecules, okay, although it's neutral, but if you look at the water, the atoms in the water molecules, there are 2 hydrogens and 1 oxygen, okay? Hydrogens have higher tendency of gaining electrons than oxygen, so, or the other way around, hydrogen have higher tendency of losing electrons, so then there's charge distribution here towards the oxygen. So oxygen will be more negatively charged than hydrogen. So in that sense, that it's actually having part of the molecular is positive and then part of the molecular is negative. So it forms this like two charge regions, negative and charge, and positive charges. So if you have a system of two equal and opposite amount of charge separated by a small distance, that system is called a dipole. Okay, so water molecule would have a dipole, and then in that case, if you have a water or another water molecule nearby, they actually this negative and this positive will actually attract to each other, so it's forming the hydrogen bonding in that sense. Okay. So a quick review of what we learned today. So we talked about electric fields for point charges. So it's the strength is KQ of the magnitude of Q over R square. This R is the distance away from the source. And then if you have multiple charges, you'll just add them up. But keep in mind electric fields, they are vectors, so we'll do vector addition. Okay. We also learn how to represent electric field just using the field lines. Okay. So that will be it for today, and then we will come back on the next time. Okay. See you guys.